let me share my screen. Okay, screen number 2. Okay, so let's take a look at the pre-assessment for lecture 13.
Doc, we're still not seeing your screen.
Can you see? No?
I cannot.
Can I see it? Now I can see it.
Okay, do you see the pre-assessment results?
Yes.
Okay, thank you. Okay, so the last lecture was the last lecture on the placement. So today we move on to CTS, clock tree synthesis. So this is lecture 13 pre-assessment. So there were 18 questions. And of the 64 responses, on average, you only miss 5, which means the average score is 130. So that's pretty good. The average score range from 30 to 180. Okay. So let's move on. Okay, can you see the slideshow?
Yes.
Okay, so as mentioned, today is the first lecture on CTS, clock tree synthesis. There will be 4 lecture also on clock tree. So lecture 13, which is today, part 1, and then the next one will be Thursday, lecture 14, which is part 2 CTS. And then we'll have lab 7, the first part of CTS. So that'll cover lecture 13, 14. So today we'll not have a labs. We'll have 2-hour lectures. And then next week we'll have, next lecture we'll have 1 hour, and then the other for the labs instructions. And then followed by lecture 15, clock tree part 3, and then lecture 16, which is going to be the last part of clock tree synthesis. And then it'll be the lab number 2 for clock tree, which is lab 8. Okay, so that's the agenda for the clock tree synthesis topic. Okay, so this is part 1. Okay, so this is the topics I put together for the this portion of the lecture. So the introduction, objective inputs, and then the pre-CTS sanity checks. And then for CTS, there's a lot of terminologies that we need to learn in order to understand the clock tree synthesis process. So there's going to be a lot of terminologies or nomenclature that you need to learn to understand those before you can before we can go on to the actual clock tree synthesis process. And then we'll talk about CTS exceptions. And then one of the more important thing is a CTS spec. And then we'll discuss the clock tree synthesis optimization techniques, what it does, how does it optimize, similar to what we discussed in the placement. And then we'll encroach upon the clock tree synthesis step itself, what's happening in there, what's the tool do during that process. And then we talk about post-CTS steps. Okay. And then we'll what we expect out of the clock tree synthesis process. And then we review the outputs, and then we qualify the CTS results. Okay, so these are the topics we'll be cover in the 4 lectures. Okay, so I just kind of briefly put the high-level CTS flow without a lot of details, just basically give you a feel of what's happening. So after placement, we do a sanity check, and then that's clean. We go on to the clock tree process. So this is just to summarize what happened during clock trees, clustering, balancing, right clock, and post conditioning. Right, that's just the high level steps. And then if that meet requirements, you go on around. Otherwise, you're going to go back. So it's similar to other steps. So it's just a flow chart. Okay, so what exactly is the clock tree synthesis process, or short, we call it CTS, right? So this is what it looked like before CTS. So after placement, you have, this is just showing single clock source. You may have multiple clock source inside your design. Matter of fact, in our lab, we have 6 clock source. So this showing just example, just one clock source. So all you have is just one pin, one clock port, and it's driving, it could drive a bunch of flip-flops, right? So each flop has a clock. So that's all you see connection directly. So this is what happened before clock tree. So CTS is the process of inserting clock buffers or inverters between clock ports and the clock pins of sequential cell, which is the flip-flops here, right? So after CTS, this is what's happening here. So you can see buffer inverters being added to balance the skew. We'll talk about the skew. What does the skew mean? To balance the insertion delay of the clocks, to make sure that the clock starting here, arrival at each of these inner flop, it may be located at different, it will be located across the chip. So we want to balance, make sure that the clock arrive at each one of these flops at as match as possible. So within a small window, okay. So preferably at the same time, but that's going to be difficult. But anyway, that's the goal of clock tree synthesis. Right. So the starting point will be from a clock source, and the end point will be a clock pin to all the sequential cells. So CTS is a very important step in physical design, because if you have poor result or QR quality result, then it'll be difficult to close timing, and you'll see why later on once we get to our lecture 203. You'll see the reason why. If you have a poor CTS results, then you're going to have a hard time closing timing or timing convergence, and also powers, right? Because your clock tree consume anywhere from 30 to 40% of your design power. So we need to be mindful of minimizing powers while we are doing the clock tree synthesis. Okay, so that's kind of high level. Give you a feel what happened during the CTS. Okay, so before, and this is after, but in between, there's a lot of steps that's happening in between in order to achieve this. Okay, so what is CTS objectives? So one of the highest priority is to want to meet the clock tree targets. What the clock tree targets are to balance the min and max insertion delay. We'll discuss what insertion delay is, and then minimize the clock skew. Okay, we'll talk about clock skew, and then to meet the clock tree design rules. So basically, so the clock tree also have design rule DRV, like max transition, max fan out, max cap. You guys are familiar with these in the DRV section of the signal, right? And then another additional we have to meet is the minimum pulse width on the clocks. Okay. Also, we have to meet timing constraints. So just like in placement, we have to meet setup. But now we have, in CTS, we'll have hold time. Now we have the clock tree, we can start look at hold time. So we'll discuss what hold time is. You guys already know what setup time is. Okay. And the other goal is to minimize power, right? Both dynamic and static. Okay. And you've learned what dynamic and static power is ours in the last section. Also, one of the goals is to minimize noise on the clock nets. Okay, because the clock nets tend to become aggressor on other nets. So we'll talk about the crosstalk effect on the clock nets. Okay, so this is the objective. There's a lot of objectives here. Okay, the input to CTS basically is the dB from the placement, right? So, but to what they are, it's just the optimized placement net list, left, def, similar the MMC timing, and then the additional one to placement would be the clock tree spec. So this is what we need to create. Okay, so this right here, usually you save as a DB and you read that in, and then you add clock spec. That will be the input to CTS. The clock spec basically is your clock tree targets. Okay, we'll discuss in detail what's in the clock tree spec. Okay, sanity checks similar to what we did before in placement. Okay, so we make sure that all the cell macro rows are properly placed. Congestions is under control. No setup or minor violations on timings is okay. All DRVs clean except on the clock nets. And then we also need to identify all the clock sources. So we know what they are. So we'll create the clock tree spec. Okay, so now let's discuss the CTS terminology. So there are quite a few terminology or terms that we need to learn. The first thing is very important is the clock insertion delay. So what exactly is the clock insertion delay? And you learn about the delay on the signal net, right? So the clock insertion delay is similar to what the gate delay or the net delays on the signal, but this is on clock nets. So sometimes it's also, some people call it clock latencies. Okay, so it's sort of interchangeable, but I think some of the people call clock latency as a target for clock insertion delay. So just throw it in there. So if you heard the clock latency is named as clock insertion delay. Okay, so what is it's a time taken for the clock signal to propagate from its source to the clock input pin of a sequential cell. So for example, here's your clock source, right? And this is the time from here, let's say it's 0, time it takes to travel to the clock pin of the flip-flop 2 or flip-flop 1. That's your insertion delay from your clock source to the flip-flop pins. So in this example, you have one insertion delay from the clock source to flip-flop 1, and then the other one insertion delay to flip-flop 2. That's insertion delay. Okay. There are two types of insertion delay. One is a source insertion delay, which is the clock delay from your clock source definition to the clock pin. So this would be the network insertion delay, right? If you do a block level design, you will have the network insertion delay. So you from your clock source. In a lab, we will have this. We will not have this what's called the source insertion delay. So source delay basically is from your clock source, like on the chip, you have an oscillator or POL which generate your clock to the pin definition. So that's the two portion. So this will happen at the SoC level. Okay. So the key takeaway is insertion delay. There are two types: the source insertion delay and network insertion delay. Okay. We will be dealing mostly with the network insertion delay during CTS. Okay, I'll stop here. Any questions or any inputs from the other instructors? Okay, so these are the key terms. You need to understand this because in clock tree synthesis, you hear a lot about clock insertion delay, okay? How it's measured. Okay, so there's no question coming. I'll move on to the next one. Okay, the other term is clock skew. So clock skew is basically the difference in time, arrival time of the capture clock signal. Okay, the different arrival time of the clock signal at two different flip-flops. The two different flop, the first one, what we call is called a launch flip-flop, which is actually launch clock, launch the data. And then the second flop was called capture flop, which is capture the data. So these two different flop, we call capture. You try to launch and capture quite a bit. So if you have a reg to reg data path, okay, timing path, this will be the longest capture. So the clock skew will be this is going to be your the difference, the common point here. So this will be the launch arrival time, which is the insert delay for this clock pin, and then the capture delay will be here. So it will be basically the time different here. So let's say this is time 0, this is 1 nanosecond arrive here, and then clock at the flip-flop 2, flip-flop B here, the data, the clock arrive at 2 nanoseconds, the skew will be the difference between 2. So 2 minus 1 will be 1 nanosecond clock skew. Okay, so you can see in terms of the waveform. So this is assuming this is the launch edge of the launch clock, and then this is the capture clock. So delay basically is the clock skew. So the goal of CTS, the goal is to minimize clock skew. So if you have a clock that go to 100,000 flops, okay, then the goal is to balance, to make sure that the arrival time at each of these flops is minimized, meaning in a small window, or whatever, if you set the target to be, let's say, 30 picosecond, then we try to achieve, the difference within 30 picoseconds. So you want to minimize that clock skew as much as possible. The larger the number, it's bad, okay? So it depends per technology. The smaller geometry, you will have smaller clock skew. Okay, so it's the clock skew is the time differential between the clock arrival of the two flops, two different flops. Okay. So do you go back to this pictures here earlier? So you can see here, so we want to minimize the clock skew across all these flip-flops. So we want the clocks to arrive at the same time, or at least within that clock skew target, let's say 30 picosecond. So if this were to be a 9 picosecond insertion delay, we want it to be like 9.03 all across here if the target is 30 picosecond. So that's the goal. Okay, so the delay here is insertion delay. So we want to match all the insertion delay for each of these branches going through each of these endpoints, right? So if the insertion delay all equal, then your clock skew is going to be 0. But that's not going to be realistic in a design. So we want to minimize the difference of arrival time across all the endpoints, all the flops. Okay, so I hope that kind of related, tied things together a little bit. Okay, so insertion delay, what this clock skew is. Any questions on clock skew? Okay. Okay, so the other important thing is clock skew can improve or degrade setup and hold times. Okay, in the minute you see, well, later on you see the how it can improve or degrade setup and hold times. Okay, so there's two types of clock skew, global skew and local skew. Okay, so let's talk about global skew first. So the global skew is the clock delay differences between two non-related flops, or basically the difference between the longest path and the shortest path in the entire design. So two non-related flops. So basically you have this branch in 1, in 2. These are non-related, meaning they're completely asynchronous to each other, right? So assuming this is shortest path here to this flop, right? F1. And then it's the non-related path here. Assume this is the longest one, all the way to F8. So the difference between arrival time of at F1 and at F8, that's going to be your global skew. Okay. And then the local skew would be related to near neighbor flops, the related flops. So for this example, F1, F2, the skew between these two going to be called local skew. Okay, so this one is a local skew. So in the entire design, your global skew is going to impact your overall timing closure, meaning how difficult it is to close your setup time and your hold time. Okay, it's based on that. Okay, so on clock skew, there are two types, global and local skew. Local is related to the two flop that are nearby that share the same clocks. Global skews are non-related flop, meaning they don't share the same clocks from the same sort. They're asynchronous. Okay, so it could be, but there's usually not related. Okay, so in CTS, we do close both setup and hold. You're familiar with setup time, so let's review setup time. So setup time is the amount of time that at the input of sequential cell must be stable before the edge. So here, so you have a clock, right? This is the active edge. So your data cannot change within a certain window before they get to here. So that's your definite setup. Okay, so now hold time is the amount of time of data at the input of a flip-flop must be stable after the active edge clock. So setup is before the active edge. Hold time is after. So this is the active edge of the capture flop. Okay. So after the data has already been captured, right? After active edge, it has to hold for this amount of time. So each of the flops will have a setup, a hold time requirement, just like setup. So it has to hold for that number, that length that is specified by the flops to ensure that the data will be latched on the next flop cycle. Okay, so make sure that it's actually output the right data. So that is the hold time. So to summarize, a flops on sequential cell, in order to make sure that the flop operate correctly, you have to meet both setup and hold time requirements, right? So if you go into the library data for the flop, you see both setup and hold time requirements for them. Okay, so before we in placement, we talk about the setup timing check. We discussed the setup slack and so on before, right? But that with the zero clock delay, meaning zero clock, there's no clock and there's zero delay, there's no clock skew. So now how do we calculate setup slack or setup timing check with the clock involved with the clock skew? Okay, so like before, when we do setup check, we check at the slowest timing library and worst RC. Right? We know setup check happen at the second active edge of the capture flops. Now you understand what the capture captures this flop, and this is the launch flop. And setup time is frequency dependent, right? So setup slack is defined as data required time minus data arrival time, just like before. Okay, so positive meet timing is negative timing violations. Okay, so where does the clock skew come in here? Okay, so the T cycle here is representing the clock period. So data required time basically is the clock period minus the setup plus the clock skew. The clock skew here between here, right? Plus the clock skew. So what is the clock skew? The clock skew, remember, is the difference between the time arrival of the capture clock and the launch clock. So in terms of T capture and T launch, so clock skew basically is T capture minus T launch. So time arrival at the capture clock and the time arrival at the launch clock. So data arrival times basically is clock to queue plus time propagation time to the combinatorial logic TPD. So that's data arrival time. Okay, so
We have a question that's come in. How does the global skew affect the timing closure?
yeah, so let's wait until we goes on to the a couple I think maybe toward the end of the slide. I'll pick up that question because right now I think if I explain it, it's going to be a little bit lengthy and explain a lot of stuff. It's going to be jumping a lot of slides. So let me hold up questions and answer to at the end once we go to when we have gone through a lot of more terminology. It'll be easier to understand later on. Okay, so just remind me to the end of the lecture. It'll be much easier to understand once we go through a lot more terminology.
All right, we'll definitely pick it up before we take the break then.
Okay, thanks, Dave. Okay, so we talk about clock skew is T capture minus T launch, right? And data arrival time is clock to queue plus the combo logic propagation delay. So setup a slack in term is data required minus arrival time. So data required time is clock period minus T set plus the clock skew, right? And then data arrival time. So data arrival time will be TQ plus TDP. So in terms of these terminology, you can see T cycle minus T capture minus data arrival time. So notice here, this is a main thing is I wanted you to see the slack and how the skew play into the setup time and check. Okay, so you see setup slack. Remember, positive slack is good, right? In term of slack. So if negative, you're gonna have timing violations. So you can see the skew here, add the skew into the as part of this slack. So keep this in mind. You see the next couple of slides why this is important. Okay, so likewise, hold time check. Okay, so the reason we want to make sure that the whole time is met is because to make sure that the flop will actually properly capture the intended data, right? To make sure that if it's not, then you're gonna have issue with the functionality. So like a whole time will be a min delay constraint, or be min delay path. So we want to make sure that we run at the fastest timing library in the best RC corner. Okay, hold check will happen one edge before the clock or before setup. So it will be the first active edge of the capture flops. And note is a frequency independence, meaning it does not matter what clock speed you at. You run it at a gigahertz, you run it 500. It's independent, so it does not care about at what speed. So the frequency does not impact hold check versus like setup. Setup it does impact, but this is important. This is very important to know. Okay, so hold slack is defined as the data arrival time minus data required time. Okay. Positive, likewise, is meet timing. Negative, bad timing violation. And all hold time violation must be fixed. Okay. I highlight red because you have to fix it. If you don't fix it, your design may not work. Unlike setup, right? Unlike setup, if you don't fix setup, some violation left, then your design still run but slower. But whole time if you have leftover, you're gonna have issue. Okay, data required time for hold it'd be hold time requirement plus the clock skew. Okay, clock skew we know what that is. And data or time is like before is clock to queue plus combo logic. Okay, so hold slack again is data arrival time minus data required time. So data arrival time is what? T Q plus TDP minus data required time. Okay, so data required time is hold plus clock skew. So the overall equation is T clock skew plus combo delay minus hold plus capture here. So if you normalize this, you'll see clock to queue propagate minus hold minus a clock skew. Okay, so notice this is minus clock skew. versus plus clock skew in the setup time. So this is very important. Okay, so I just define here only in terms of the waveform here. I think you can plug in the numbers and see how it works. Okay, so let me go on the next slide. I think it's going to be important how the clock skew play a role in the setup and hold time. Unless the other instructor have any more comments and maybe explain it better than I do. Or any questions from the students on the hold time check? Because this is the first time that we introduce hold time to the class. So keep in mind, there's a whole setup check requirement, there's a hold time requirement. That's for each flip-flop. But in the overall design, we have to make sure there's a hold time for for the entire for every flip-flop in the designs. Right. So each flop will have a check. So if you have 100,000 flops, all 100,000 has to meet the hold time checks. If one failures, then the failure could propagate downstream and cause logic issue and function issue. Therefore, your design may not work. So that's why it's very important to fix hold time, all the whole time. Okay, there's a concept of positive skew and negative skew. Okay. So what is positive skew? Because we learned about clock skew, right? Launch, capture. So you have a insertion delay for the launch, insertion delay for the capture. So the difference between two is the clock skew. So positive skew means happen when the capture clock arrived later than the launch clock, which means here you look at this launch clock. It's got 3 buffers, right? So and then the capture clock here, it has extra buffers. It had 2 more buffers going through. So the capture will have a longer insertion delay, which means it's arrived later than the launch clock. This is a positive skew. So you take the capture minus the launch. Remember, that's the skew for the 2 flops. So if that number is positive, we call it positive clock skew, meaning that the capture clock arrived at a later time than the launch clock. Okay, so here waveform representation. Clock at flip-flop 1 start 0.0, and at some later time here, there's a delay, and it's arrived at flop 2. So that is a positive skew. And the positive clock skew, remember I mentioned earlier on the formula, is basically positive skew improves setup time, right? Remember the setup of slack. Remember this formula, it plus the clock skew, capture minus. So if you have positive, that means you have more slack, right? So because it's arrived later, you have more time to do your setup. So positive skew improves setup timing. Okay. I'll pause here to let you guys think about it. Okay. Why is if you have, so you may ask questions, then why don't we just have positive skew all the time? All the flops, right? So look like here, set slack, the bigger the skew, the better the slack will be, will help set up time. Why don't we have a large clock skew? Does anybody know? Why not? You can chime in the chat before I go to the next slide. Okay, so no work ties will make the whole slack worse. That's correct. That is correct. Because yeah, you can see the formula here, right? Exactly. That's also true. Yep. It also makes your chip slower, correct? So, okay, so the other is the negative skew. So a negative skew is opposite, right? So basically meaning that your launch clock arrival early, your launch clock arrival earlier than your capture clock. I'm sorry, the other way around. When your launch clock arrival later, after, so the capture actually the insert will be shorter. So you have a negative. So here we go. This insert delay going to be on your launch clock be much longer than a capture clock. So then your T capture minus T launch would be a negative number. So remember, so this can lead up to setup violations, right? So you can see if the larger than skew, you're gonna have setup violation, which means your design can run slower if you have a lot of negative skew. However, the negative skew does help hold time, right? You can see the formula here, right? So you can see here on the waveform. So hold check would happen here at the first edge here at the flop two. So it's actually here. So you have a lot more, you have much easier time to meet your hold versus later on down here. Okay, so remember your formula here. Okay, so the key takeaway from this slide is negative skew, improve hold time, but bad for setup. Okay. Positive skew is good for setup, but bad for hold. Okay. So you have to balance between the two. Okay, so this is a very important concept for closing timing post CTS, meaning post CTS meaning after clock tree is in. Okay, so we need to understand this so that when you do your labs or do your final project, you need to be able to make trade-off and understand why. So if you have a particular path in the design, how do you go about fixing setup and hold? Because you can have a path that can straddle both setup and hold. If you trying to fix it up, you break hold. You're trying to fix hold, you break setup. Okay, so there are those called straddle path or conflict path that you'd be able to fix. Okay, so there's some questions from we want to improve hold and setup time. We want to fix all the hold time violation, all of them. That's yeah. Yeah, we also want to close all the setup time. So whatever the targets that that is set for, we want to close all of it. But in the event that you have a choice, you want to close all the hold first. That's priority in terms of timing. Because if you don't close all your hold time, fix all your hold, your design won't function. But if you don't fix, you still have some minor violation on your setup. That if you can't fix, you have to leave it one or two, leave setup because it just if you have violation setup is frequency dependent. So therefore it just runs slower. But if you close all your hole, your design still function. But if you don't, you fix all your step, you leave hole, then your design won't work. Okay. So let's go up to yes. So the clock skew equation is still the same, correct? It'll be the capture minus the launch. So either that's correct. So the equation is the same. So if this is let's say this is arriving earlier. So let's say arrive at 1 nanosecond, and this is arrive at 2, then 1 minus 2, you have a minus 1 clock skew. That's what we call negative skew, right? Versus positive skew. So positive skew is you have the capture arrive later. So 2 nanosecond and this arrival 1, 2 minus 1, you have 1 is positive. So yes, the skew equation is the same. Just the capture minus the launch. Okay, so what if CRPR is enabled? How clock skew is? So remember, CPPR is a clock pessimism removal. So what that does is, if for example, if this portion will be this will be the CPPR, the clock pessimism removal. This will be removed from the equation, from the timing calculations. Okay, because launch and capture can't have different timing on the same path, so this will be removed. Yeah, so that's a good question from Kanyu. Yeah, so this will be removed from the equation. So in your lab, we do have the CPPR, the clock pessimism removal on, and you will see in the timing reports on the detail, on the summary, you'll see that CPPR will be removed, be adjusted from the skew. Okay.
But can
Right.
you mention OCV for that CRPR? I think that's related to OCV.
Yeah, you Phil, you can go ahead if you're thinking about it. I have to switch gear. You can go ahead and please.
Yeah, I think the CRPR is related to OCV on-chip variation. So on-chip variation adds, extra delta delays on each and every gate. So in this clock path, you have the clock with 2 buffers on the left. So maybe I should just annotate. So each of these gate will have a delta delays because of OCVs, right? So CRPR means that since these two are common, so in calculation of these different paths, the delta OCV on these guys are removed. That's what it meant. So because on when you do the clock, the propagation delay, so clock, all these gates are in propagated mode, meaning the common delays will be the same regardless of CRPR is turned on or not. But CRPR relate to OCV, which is an advanced concept. Maybe it's not covered in this basic class. Yes. Okay, that's all.
Okay, thank you, Phil. Okay, so yeah, I was guys, new message. And you can say set up flag T capture minus CPR. The CRPR is that adjustment value is yes, it's going to remove from the equation. That's right. Yeah. So there'll be a CCR adjustment. So the tool will calculate that based upon the library and technology on the path. It will know the value, so the per path per technology, and based on the number of level of logics that is common. So those values can change based on the number of logic and technology. So yes, those will be removed. The C clock path and CPPR.
Yeah, I'm not sure that equation makes sense. What is CRPR in this equation? That
Yeah, I think he's referring to this clock pessimism removal, CPPR. So yeah.
Yeah, again, it's related to OCV. It's not something of this nature. But anyway, I just want to make sure that we understand it correctly.
Okay, let's Okay, so the next couple of terms here I put together is the other one is clock uncertainty. So it basically is you hear that term uncertainty. You can uncertainty meaning that not sure, right? Not sure where it is in English. So clock uncertainty mean basically is used to specify window within the clock edge can transition. So this is used to usually model the clock jitter. So your ID clock source. Um, well, actually, let me use model clock jitter, clock skew, and as addition up, and also we use as additional setup and hold margin. So let me show you what the clock jitter is first. So clock jitter is a deviation of clock edge from its ideal source. So this is ideal clock. So the jitter, it can go uh, uh, faster or slower, right? So it's just a jitter. So this is a waveform example of what the clock jitter look like. The source usually for clock jitters is the crosstalk, and we'll talk about crosstalk later, and also noise and thermal effect from of the clock source. So thermal effect meaning supply voltage variation or temperature variation. So so clock uncertainty is used to model the clock jitter. Okay. So also use addition setup margin and hold margin. Okay. So setup margin and hold margin, usually in a design managers and so on, they like to have safety margin. You know, we'll add some margin around the setup and hold. For example, you need to you know, the close hold time at 10 picosecond, and they may want to set up as 20. So if you call it 20, you have 10, so you still need 10. So it's just a safety margin you used to add in, same for setup. Okay. Clock slew is also known as a clock transition time. I think we learned about what transition time is before. So slew is just another term for transition time, because slew rate is how fast the signal rises or rises from a low to high low. So it's usually registered at 10 and 90 for the clock. Okay, so for example here at 10% 90, so the slew rate will be the time it reaches 90, and this is input slew for this signal. Okay, so that's what the slew rate is. So you hear clock slew, basically mean the transition time, how fast it rises, because the clock transition time is important in determining how clean the clock edge is, and how fast the clock can get to the clock pin input, which means insertion delay. Okay, so that's what the clock uncertainty meant, and also clock slew. Okay, we already talked about clock jitter. Okay, next one terminology you hear will be clock duty cycle. So what is clock duty cycle? So a duty cycle of a clock is defined as the fraction of a period of clock in which the clock is inactive. I mean, the clock is active. So to put it into an equation, so this is duty cycle is equal to a fraction of a period of clock in which is active, which is here in the waveform. This is the waveform. This is the clock. So active is during high. So this active high T on over the period time 100%. So for example, let's say the period clock is 10 nanosecond, right? 10 nanosecond. And then my active period is 5 nanoseconds. So 5 over 10, which is T on, period, 10 period, 10%, so 50%. So in this case, this waveform here is a 50% duty cycle. So which means you can see it's equal rise and equal fall. So when you have an equal rise, equal fall, we call it a 50% duty cycle. Okay. Okay, so as far as the 20%, so this example here, you have the clock is active only 2 nanosecond out of the 10 nanosecond period. So this is considered a 20% duty cycle. Okay. Likewise, you can see if it's rise at 40, then it'll be a 40% duty cycle. Okay, so that's what a duty cycle is. Why do we care about clock duty cycle? Okay, so duty cycle degradation or variation impact timing and can usually impact on a half cycle path and minimum pulse width. And we'll talk about half cycle path and minimum pulse width in a minute. But it does have the impact on those. That's why we talk about duty cycle. You hear, from here, preferably we want a 50% duty cycle, right? In clock, but that's not going to happen. That's the idea, right? In reality, you have impact of OCV and also the impact of PMOS and MOS not being equal and rise and fall not equal, so it will get distorted. So what causes duty cycle degradation or variation? So variation in rise and fall along the clock path. So you have, if you have the rise and falls not equal, it's going to get impact. Also due to OCV. Okay, so but everybody understand it as if somebody said, okay, we 50% duty cycle clock or a 60% duty cycle clock, in your mind, you should have some sort of shape, understand what that meant. So you can 50, 20. So you can see, yeah. Okay, so remember we talk about duty cycle impact minimum pulse width. So what is a minimum pulse width? So all sequential cell elements in design must have a minimum pulse width requirements for clock signal. So all the clock signal that goes through all the flip-flops have a requirement for minimum pulse width. So why does this have to have, this is a pulse width, by the way, so clock. So this is a pulse width. So it's a 50, if this was a 10 nanosecond period in a 50% duty cycle, the pulse width would be 5 nanosecond, right? So meeting this requirements, the reason is there because it makes sure that there is enough time for the internal cells to actually does its job to meet the to get the logic out to the output. So there's minimum requirement. If it's not wide enough, then it would not function correctly. Okay. So after CTS, once the clocks are in, there is a minimum pulse width check to make sure that the width of the clock should be more than the minimum pulse width requirement for that particular flop type. Okay, so this happens CTS. Okay, once the clock's in, so in placement you can't do this because in placement there's no clock. The clock tree is not in, so we can't check that. Okay, so all the clocks must meet the minimum pulse width requirement after CTS. So that is one of the check that must carry out to make sure it's on it's meet. Okay, I think I see a question popped up. I see let me go up to see who has this question. Folk is said I only see 50% duty cycle is used in the school project. Is there any case we use different duty cycle in reality? No, ideally we want a 50% duty cycle, right? That's the I have not seen where you don't want it. The reason is the if it's not 50, it's going to impact it may help set up and it'll impact your timing. Basically, it'll be much difficult to close timing, and also it also mess up your flops. It impact the function of the design. So ideally, we want 50% duty cycle. I have not seen where you don't want to I have not deal with not non 50-50. Other instructor and field taking rule. You guys see any reason? Have you guys experienced with the non-50 duty cycle clocks?
Yes and no. Like you say in general, because you do one edge, right? So rising to rising, that's one cycle. So, but sometimes you have half cycle pass for some weird reasons, right? So when you have half cycle paths and one path is, say, rising to falling needs less time than falling to rising, then you intentionally skew one edge. But that is rarely, that is not done in the normal flow, right?
It's
That's
not.
only in custom circuits only. And I've seen it implemented in some weird cases. Yeah.
Yeah, that's more event in the custom stuff, but yeah, okay. All right, thank you, Phil. So and Phil I mentioned about half cycle path and minimum pulse width. Okay, so let me see, okay, so okay, I think it's a good place to stop here for a break because there's next several slides. I think we actually go much faster than anticipated on the clock tree.
Bach, let's go back and get that one question that came in first of how the global skew affects the time enclosure. Or should we wait
Yes,
till
yeah. So for example, that's good questions. Let's go back. Remember the positive skew, negative skew, right? So on the global skew, if you have a large skew, right, a large skew, that's going to impact your whole time, right? It does help your your setup, but on a large one, if the skew is huge, then it'd be difficult to close. It'd be difficult to close setup the whole time because of the it happened to be on the same skew groups. We haven't talked about skew group yet, but if the global happened to be on the same skew group, then it's going to be hard to close on the setup time, right? So it's also dependent. There's positive and negative, right? It's dependent on each. But basically, if you have the smaller skew, it's much easier to close timing versus a bad clock tree where you have huge clock skew. Does that make
Yeah, I want to add.
you
right,
want to
that-
yeah, Fuma,
yeah.
you can
Yeah,
explain better than I can.
yeah. I wanted to add, there's a difference between global skew and local skews, right? Like we covered, local skew is a skews between flops that are timing related, meaning they are passed between them, right? So that will have an impact on time enclosure setup and hold time. If you have skews between related flops, meaning there are paths between them, then the skew will impact setup time or hold time.
Mhm.
But if you have global skew means, yeah, there are skews between, say, the longer path on the red down here and the shorter path on the pink up there. Since the flops do not talk to each other, in general, it should not affect anything, right? Any timing, because they are on different trees, so they are not optimized or they're not related. So the skew on one doesn't have any impact on the other. So I just want to add that in.
Yeah, there'll be in different skew groups. They'll be asynchronous to each other. So
Yep, precisely. Yeah.
okay, so let's take. I think we on the fast pace of. Can we take a 10 minutes break? I need a bio
Yes,
break.
everyone will be back at 10 after 10. I'll get a clock started for you on the screen.
Hey, Dave, thank you.
No problem.
So, okay, let me share my screen. Okay, can you guys see my screen?
Yes.
All right, hopefully everybody a good break. Okay, this let me see. I think the questions just popped up. Let me see how to get back to the chat. I saw it earlier. There we go. Okay, so global skew impact because well, we need global skew. Okay, the global skew, actually, if you think about at the system level, right, level up, eventually those will become, if you have a huge difference, it's going to cause issue at one level up because eventually all the clocks are on the going to be one clock source coming in. So at the higher level, so at the block level, we mainly at the chip level, we mainly focus on the low local skew, but think about system level. So we need to have the overall. So I think that's the reason that you think about one system up, right? You got a balance for those. So let's see. Global skew doesn't impact time between two block, but still over time and design costs. Yeah. Okay, yeah. So the whole design, right? Yeah, it's the whole design, but also the thing about the system level, one level up, right? If you have one short, one long, you're gonna have a hard time of closing timing at the system level, and also think about the overall performance of the this SoC. So that's the reason. So just think about we focus on the local, right? If you have once you move one level up and then at SoC level and they connect to your design and you have one long, one short, but at the very top, that's going to be the same um the same source was the same skew group, then you have issue. You have one long, one short. So in the same manner.
Yeah, I want to add something. Sometimes the long skew is unavoidable because there's a relationship between the skews and the latency. Meaning sometimes for very large clock trees, meaning that there are many flops in one clock versus the other. Say, can you put, you go back to the global versus local skew? I just want to add something.
Hold on, let's bear with me. This
Yeah, so here, for example, the top tree, say there are 3 flops, but the bottom trees, there are 1,000 flops, right? Typically, when you do CTS, the tool will try to minimize the skews, right? The local skews, because that has an impact on timing. But if you have a very large block trees on the bottom, say 1,000 flops versus 3 flops, 3 flops, you can have very short tree and you still have very good skews. But when you have a huge network of flops, then to have the minimum skews, you force to have a long latency, meaning you have many buffers divided all these load into something manageable to get a good skews. So your local skews on the bottom might be small, but if you have only 2 trees, one is small and one is large, then you are forced to have very large global skews. You don't want to balance them. You don't want to make the two the same. So that's why sometimes global skews just for your information only. If you look at and you have a huge global skews and you say, hey, these are about the same number of flops, what's wrong with the bottom one that has a long skew? So you might want to shorten it and still don't sacrifice the skews. But the benefit of that is you have shorter clock trees, still good skews, but less area and less power consumption, right? So those are the things that you can have in mind as well. So that's all I wanted to add.
Okay, thank you, Phil. So where were we at? We were at duty cycle, minimum post width. Okay, I think last we spoke was we talked before we left for the break is a minimum post width check. Okay, so our clock must meet the minimum post width requirement. Okay, so how do we have post width violation? How do we minimize? How do we fix them? So to minimize is upfront, of course, we want to use if we use the balanced buffers or all inverted tree types, that will help minimize the post violation, meaning that it will maintain it have better chance of maintaining the equal rise and fall time. So therefore, it will help trying to minimize. But what if you have post violation? What are some things you can do? So here in this example, I have a clock path that has 20 buffers, okay? And assuming that I have a clock periods of 500, 1,000 picoseconds is 10 hours, it's 1 second, okay? So the rise is 500 picosecond and the fall is 500 picosecond. So this is ideal, right? So let's say that each of the buffers here, the rise and the fall is unequal. So each time it goes to the rise, it will eat up 10 picosecond. So by the time, let's say go to first buffer, the rise is gonna be 490. So after 10th, so each buffer eat up 10, then you only have 400 picosecond after the 10th buffers, right? So knowing that each buffer is eat up 10, you can fix it by add inverters in here to invert the signal back at the buffer 11. So now the buffers now will eat up the this the 400 the rise. Then it eventually by get to 20, then it'll be 500 again. So 600 become 500, and then you invert the signal back. Then you have the original signal, the buffer, the clock signal that you started with. So that's one of the way that you specifically or strategically place the buffers in to fix the pulse width. Until you guys know any other method to fix if there's issue with the mid pulse width.
No, I don't really deal with this kind of stuff. Right. So, but I think the tool just fix themselves. I never have to deal with this manually.
Yeah, so that's right. In reality, we have EDA tools that actually checked for us, and by having knowledge what mid pulse width violation is, and and then the tool will fix it for you. But in case it can't fix it, you have to have the knowledge to see, okay, what's happening and debug the problems, and then may have to fix it manually. But by understanding how it can be fixed, it'll help your job. You'll be a better engineer rather than just depend on the tool, but you have to understand the knowledge. But this is one of the methods that you can actually fix it. Okay. Yeah, I'll leave here for a few minutes for you guys to digest. It's a lot of waveform. Okay, this is the same. Go ahead.
There's a new question in the chat.
So how's that can we reduce the skew by providing multiple clock source instead of one clock source, sir? So the clock source are dictated by the type design. You can't just add a clock source where you want it. Okay. So it's already by the time the design get to you, it's the clock source already fixed. Okay. So the design, by the time synthesize, we should already know the number of clock source. So you can't just freely add clock source in there in your design.
Yeah, think of physically how are clocks defined, right? Are created, right? Typically, it's by having a crystal oscillator, right, or an on-chip phase lock loop. So you cannot just create, and if you create multiple clocks, how are they generated on the chip, right? Right. So you cannot, but you when you create multiple clocks, you just creating virtual clocks, but not physical real clocks.
Yeah, I think maybe Ngô and Tan Hao thinking about if your design has 100,000 flops, and can you like let's say you have one clock source, that driving 100,000 flops, maybe divide up to 10, and you instead of balance 100,000, each of the balance only 10,000 versus 100,000. I think that's what he's thinking, doing similar to yeah. But unfortunately, I mean that is probably true if you have, it's easier balance with less number of flops in your sync pins versus 100,000 for sure. But
Oh yeah,
unfortunately,
right.
yeah,
If I can add to this, and this is a question from Ngô, Tai, and Hao, right? This is a very, very good question. So at the SoC level, when we architect the chip, this is called the SoC architecture, right? We define the clock architecture. And for a big design, what we typically partition in multiple subsystems. And the most likely there will be a different clock source for those subsystem. And there will be synchronizer between the when the clock cross the boundary. What you mean, like two different clock source, two different so that they operate asynchronously. So you need a synchronizer. So that is one of the way to minimize the clock skew. Even in some of the subsystem that's very large, especially when you have the chip, like a subsystem that have like half billion transistor in there, you definitely want to partition I mean a different clock branch in depend on the the number of blocked in or component in that subsystem. And give you an example, like if you have a subsystem that has like a machine learning block, with typically pretty large, and you probably want to have a dedicated clock for that block by itself, and not sharing that with like the bus interconnect that block connected to. That's just one way to minimize the skew. And so the answer, yes, we at the SoC architecture, we do architect the clock tree, partition the clock in multiple subsystems. And there's a penalty for that, because anytime you add that synchronizer, meaning that you add more delay when those bus master or bus initiator had to access from one to the downstream memories or peripherals. Hope that answered your question. I think it's better to have the diagram. I mean, draw a diagram. If I can do one, I share it in the next class. Or I can stick it here in a chat window.
Yeah, but I want to stress the importance of understanding on an SOC, right? So you have an SOC, so you really just have the whole chip like this, right? There's a huge chip, right? And typically you have a crystal oscillator off chip that generate the clocks, right? You only have one source, right? And in here you can do a divide by and divide and partition into clock 1, clock 2, clock 3, but each of these clocks will be a different buffer, for example, and you can create a clock at the output of these three, and you can have clock 1, 2, and 3 either same is the same frequency or different frequencies, and then each of these three are independently synchronized to each other, meaning that you have clock skews group. But if you're talking about the tool, and you can create a clock here, and the tool will automatically build all these trees for you. So there's no need to create all these things manually, right? So that's what I meant. Because the tool will break all these things based on your skew group definition and all, and they do a much better job than just do manually. Because if you create a clock here and clock here and clock here, right? So first of all, you need to make sure that there's no pass between them, right? Otherwise, you put a synchronizer between them. But since it's not necessary to address what you're thinking of, but can we reduce the skew? Right. So the question is, can you reduce the skew by ngô thái hoàn hảo? Then the answer is no, don't do that. Reduce the skew by using the CTS tool, and it automatically reduces the skew for you. Instead of, if you do it manually, you run the risk of not modeling clock correctly, because you're creating virtual clocks over here, but in reality it's only one source here with a physical crystal oscillator, or you have an on-chip PLL that only drive one output. So
Okay, thank you, Wu. Thank you, Phil. So yeah, we haven't talked about skill group. Well, I think next couple of slides we'll talk about skill group, and what it meant. Okay. So bottom line is you cannot introduce new clocks in there, but you can define skill groups based on your knowledge on the design. Okay, on your clock trees, on your clocks. If you understand those, you can define them. There's more question coming, I think. Do you cover clock gating? Yes. So hold on for, I think is in this in this lecture. So okay, let's move on to the next one. So okay, we talk about how the duty cycle impacts half cycle path. So what we've been talking about timing, right? Setup and time and hold time. We've been talking is called what's called single cycle path. So single cycle path means that it has the entire cycle. Let's say the cycle is 10 nanosecond. It has entire 10 nanosecond to for the data to make it to the other side. So here, so the true definition is a single cycle path is a path which requires full cycle to capture the data. So data is launched from a flip-flop and captured by another flip-flop at the same edge, right? Pause edge is pause edge. So if it's negative, you usually have a bubble. Okay, at the same edge. Pause edge to pause edge or negative net edge. So positive edge meaning positive trigger flops versus negative trigger flops. There's two type of edge trigger flop. There's positive and negative, meaning that on the rising edge, it's trigger, and then following edge, the trigger is negative. So setup and hold check occur within a single cycle. So for example here, launch clock. So and capture clock. So setup, check at the second active edge of the capture, and then hold at the first edge, right? So that is the single cycle path. Normally we talk about timing, closure, setup, and hold. Normally it's a single cycle path, but there are certain situation that you have a half cycle, okay, which half cycle path may require only half a cycle to capture the data. So this happens when the capture and the launch flops are at the opposite edge, whether it's positive negative edge or negative positive edge. Okay, so if you take a look at this particular a half cycle path, so the launch flops is triggered by a negative edge, denoted by this circle here. So this is in the industry standard pretty much. So if you don't have a bubble, that means it's a positive, but when there's a little bubble in front of it, that means a falling edge or negative trigger flops. Okay, so if you look at the waveform here, so this is the waveform for the launch flop. So since this to be a negative, right? This is a positive, it starts 0. So at a half cycle, the negative edge happens. So this is where the data actually get launched at negative edge, not here. So you can see since it's launched here at the negative edge, you already lost half of a cycle for the setup, right? So you now you have to meet instead of 10, now you have to meet at 5 because this is the launch edge, and now this is the capture edge. So you really only have 5 instead of the entire cycle for the setup to make it, right? Okay, so that is why the duty cycle impact the setup and hold, right? If the duty cycle was here, if it's 70% duty cycle, then you really have only 3 nanoseconds. So that's how it's impact the half cycle path, right? So it was at 50, then you have extra because in the half cycle path, your setup is actually get cut by half. That's what I call half cycle. So you can see how the duty cycle impact the setup time, right? So it's 20, you cut by 20, but if it's further down here, 70, then you actually cut it off, reduce it furthermore. However, on the other side, the whole time now is relaxed, right? So here, the whole time is checked at the first edge of the capture active. So it's actually here. So it actually relaxed by half a cycle. So hopefully you see how the duty cycle impact the half cycle path and how the timing for this half cycle path works, where you check it. Okay. Question, comments? Okay, let's move on. We have about, I think, 7 more slides. Okay, now the next slide is clock skew group. I think we kind of allude to the clock skew group earlier. So what is a clock skew group? So basically, it's a group of clock sync pins. We'll talk about clock sync pins. So each of the flops, the clock pins of each of the flops called sync pins, which needs to be balanced against each other, meaning that we only balance a group of similar clock from the same clock, from the same the synchronous each other, meaning they share the same clock source. So that's why understanding the clock structure of your design will help you to how to group this, will help the CTS tool to better balance your clock tree, therefore will achieve better clock skew. So by default, the tool will just put everything in one groups, okay? It'd be just put in group 0, one group. So understanding the clock structures of your design, you can define a different groups. For example, here, so group 0, 1, and 2, right? So you know that group all the flops in that related, then you group together one, so the tool just balance it against each other versus okay. Likewise, group 2, group 3, but each of the group need to be within the group. They need to be synchronous each other, meaning they're driven by the same clocks or some sort of clock-heavy relationship. Okay, I mean synchronous. Each group are logically exclusive to one another. Exclusive mean not related. For example, here you have clock, say group 0, you have clock 0 on scope 1 will not be balanced against this clock over here or clock 1 over here. So they're completely unrelated, unsynchronous each other. Okay. So if you go in, you define the clock groups, understand it will help the tool balance it better, right? Instead of having one giant group and have so many sync. So this is what Phil was alluding to earlier. So we have different groups, we reduce the number of flops or number of syncs, then therefore you achieve a better skew per groups. And okay.
Yeah, and unless you are a logic designer, you wouldn't know, how to create all these groups because you need to understand the functionality, right? So,
yeah. So you see, you can look in the SDC, the MMC file, and or you can write it out, and you can understand. It's very important. You have to understand the to build a good clock tree. You need to understand the different understand the clock relationship in your designs. Okay, then you can achieve much better clock trees and have much easier time closure timing. Okay, makes sense. Any questions? All right, let's go on to the next one. Clock buffers versus regular buffers. So I think you guys understand the regular buffer. So the clock buffers are designed to have equal rise and fall, meaning 50% duty cycle. Okay, so meaning that if the rise and fall should be equal, like this, right? This is rise, fall. So the clock buffers are designed to be that. Okay. The regular buffers, however, is not. Okay. So may have unequal, right? So in the clock buffer, usually the P transistor are much larger than the N. Okay, and that's N transistor. Okay, if you understand the physics, the N transistor is got holes, so the mobility is a lot. It has more mobility versus the other one. Electron, I mean the hole on the P versus the electron in the N. So the P mobility is less, so therefore the transistor has to be a lot bigger. But anyway, that's another topic. But knowing that the clock buffers are designed to have equal rise and fall, right? So therefore, it's easier to maintain the duty cycles. Okay, so do you want to use the clock buffers or inverters for CTS on the clock trees? Because it'll help you avoid the minimum pulse width violations. You could try to maintain the equal rise and fall, therefore the less distortion on the duty cycle. Okay, I put here is in a low geometry node, clock will have input outputs on the higher metals. Okay, yeah, so on like a 3 nanometer, 4 nanometers, the clock buffer, in addition to this, it'll have clock pins on a higher metal level, meaning like usually pins in the metal 0, metal 1, there'll be like sometime on metal 2. Okay, so it's better distribute the clock, distribute the drives and drive the clock nets. Okay, so do not use regular buffers in your clock tree because it could have it'll create minimal pulse violations. Okay, you get distorted if the duty cycle is like 60-40, most likely the 40 is going to have pulse violations. So in CTS spec, you specify which buffers and inverters you want to use. So in the library and technology, there will be regular buffers and clock buffers. And clock buffer usually is, you have a destination like CLK or something like buffer and CLK inverter, something like that. So you need also, when you do design, you need to look at the libraries and understand, look for buffer inverters and understand the clock buffers and what the naming and so on. So you can specify that in your during a CTS. Okay. Otherwise, CTS would just use all the buffers available to it, which is not good.
And question for the students. So for CTS, you use clock buffers. For timing optimization, which one, the clock buffers or the regular buffers are better for timing? Clock buffers or regular buffers? Please put the answer in the chat. Which one is better for timing closure, is faster, and why? Maybe you just say which one is faster. Clock buffer is faster. Anybody else? Clock buffer. Clock buffer. Thank you, Nguyễn Vũ Thanh Anh, Nguyễn Văn Duyên. The answer is not. Clock buffers are slower, right? Yeah, so Lê Thanh Trung is right. So the reason is this. So you see this already written down here, right? See, like Bud was mentioning, so if you have an N and a P for, say, a buffer, meaning the two inverters, right? You have a P, and usually the P is quicker than the N. So if you want to pull down fast, say you have one X here. So in order to pull up, fast the same rate, then you have to have typically about 2x here of the double width, because the P is weaker than the N, right? So but because you have the rail and you have a fixed pitch, a fixed what do you call, number of tracks, usually it's not economically good to have so big of a P transistor. So typically the P is sized for the optimum area. The P is sized so that the rise time is kind of slower than the fall time here. You see that? So but in order for the clock buffer to have balanced rise and fall, then it has to match the slower one. So that's why this slow, this instead of being fast, because if you be fast and you don't have balance, so yeah, you make the fall time slower. Therefore, if you look at the entire buffer, you from one edge to the other, right? This is faster than having the clock buffer where you intentionally slow down all these edges to have a 50% duty cycle. So that's why typically when you build a clock tree, you choose all the clock buffer CK or CLK prefix, and with the clock name prefixed by something that indicative of clock buffers. But when you fix timing, you don't want to use this. You want to use regular buffers because they're much faster for the areas that you're given. So it's important to know. Yeah, you don't want to use clock buffers to fix timing issues. All right, so the answer to my question, why we don't use clock buffers in our case, a simple reason: they intentionally make it slower. So they're bigger, more power hungry, and slower. So why you want to use it for fixed timing?
Yeah. Thank you, Phil. Yeah, they're bigger and slower, and they take up more spaces, therefore cost, higher density, therefore could cause congestions and so on and so on, right? Okay, thank you. So that's about about clock buffers, regular buffer now. Okay, somebody asked about clock gating. So clock gating is a technique that used to disable clock to register or flip flop or idle to save power. Gating usually is compromised latch and an AND gate, which can be integrated on ICC cells. Okay, so this is usually ICC cell. I think we talked about the ICG cell before, and also the clock gating, the traditional gating where it's just an AND gate where they create glitches. So if you have any clock gatings, it's going to be ICC cells, okay, because it avoided glitches. So benefit of clock gatings reduce dynamic power. The disadvantage of clock gatings is increased clock latency and skew. You guys think why? Right? Remember we talked about insertion delay and so on. So you're adding extra logic in between on the clock between the clock, right? So it's also slightly increased area. Okay, so there is a clock gating check to make sure that it meets both setup and hold time, so that the clock will probably without glitches through the capture flops. There are two types of clock gating check. Well, there's two types, active high and active low. So active high meaning it checks during the active high and active low here, right? So what dictate that? If we're using an AND gate or an AND, the same thing, the gating cell, because active high will let the clock when this is active high, it will propagate the clock through the capture to the capture, right? Active low because of an OR gate, and it'll propagate. So we still need to do a whole check and setup check to beat before to make sure there's no glitch propagate throughout. So let's see, this is okay. Actually, this is I have, yeah. So during the check for active setup for active high, we don't want the signal to switch during high. We want the signal to change during the low side. I think this is this slide. So this is the better slide here. Yeah. So this is the active check for the clock gating check for the active high. So you can see here, right? This is actually a half cycle path. So usually it's implemented with half cycle path to meet timing. Remember half cycle path? So on the falling edge, you can see here the signal changes here, so you can actually meet the set and hold both on this. If you have a full cycle path, then you have problem with meeting whole. Okay. So this particular check. And Phil, do you have a better way of explaining the clock gating checks than what I just mentioned? It seems like
I think it's good enough for if you look at the NAND gate, right? So yeah, you want set up so that you won't have a pulse, right? You don't have a glitch, right?
Yeah.
Right. There's a question from Nguyễn Lê Minh. Yeah, might want to answer that.
This clock gating then is so small that we just use it to the yes. So yeah, so the gain is much larger than the disadvantage. I mentioned that there just to know. So usually when people use clock gating, they don't really think about the disadvantages. They think the gain is far more that outweigh the impact, the negative impact. So saving power is important, right? Because yeah, because if you have the chip is power hungry and they can also burn up your die and you need heat sink and so on, so different packages, so that's impact a lot of things. So saving powers and keep your chip cool is far more important than some of the added area and things like that I mentioned.
Yeah, and also it's just for your awareness, but the tool can fix all the issues, right?
Yeah.
So you must use cocktail gating because to control the power. There's no question about whether or not they should be used for power sensitive design.
So yeah, I mentioned these. It's just for you. I mean, the area is very slightly few gates here there and there compared to that, and then it will increase it, but the tool make adjustment to balance it out with the rest with the path that doesn't have clock gatings. So the tool will know about it.
Do you want to mention integrated clock gating cells? I think it's important for PD guys to know that.
Yeah, I think I mentioned in the placement on the slide the ICG cell. So basically, this is the one of the ICG cells. So in the ICG cell, basically create with the latch and an AND gate. It's compact. It's a custom built cell. It's a one cell, right? So if you were to have these as a separate before, you have a lot of it's hard to control these timing, and so you have a lot of glitches. So they create this one cell so that it's fixed and a latch fixed together. We know the predictable timing here, so it's easier to close timing and with the ICG cell. Avoid a lot of issue with the glitches. So we mentioned that in one of the slides in during placement.
Yeah, I encourage people to study more about integrated clock gating cell (ICG) because you almost have to use them instead of discrete components to build clock gating.
Yeah, so pretty much most of the libraries now will have the ICG cells, especially in the lower node. They'll have ICG cell now. I mean, unless you use some really old technology that doesn't have it, but yeah. Okay, NDR rules. So terminology you hear start with the clock with actually in a lower geometry, 3 nanometer point, the NDR rule actually appear during placement, but here we talk about in CTS because it's where we're gonna apply it. So NDR stands for non-default rules. Basically, in the technology, you have a specific routing rules and so on, but NDR rule are the rule that we specify as an extra on top of in addition to what the technology is. So for clock tree, it's important we apply NDR rules. For example, this is a default routing rule. So net one is one width and one spacing. So meaning that this, say one width, let's just make it simple. One micron is, one space is single space is 1 micron. So it's 1 micron. So these are the default. We want the clock to be much wider and we want the spacing to be double, right? So we apply the NAR. We said, okay, we define NAR called double space, double width, to 2 micron and 2 micron, 2 micron. So we define that we can define 3 or 4. It depends on us what we need. So we define these particular rules, user-defined rules, right? And then tell the router to use that rule on certain nets. So the NDR rules not only apply to clock nets, you can use it on signal net, those critical nets that you want to have extra spacing, extra wide. Okay. So you can also apply shielding. So there's rule that you say, okay, I want to shield it, either side with power and ground on either side. So you can define that also. I don't have it shown here, but you can look it up. But you can also define shieldings as part of the NL rules. So example here, I just do double space and double width, but you can do whatever that is applicable to your design, or you wish, 3, 4, but just remember, it take up a lot of routing resource, right? Because if two space, you can see it take up double the tracks. Actually, more than that. This 2 track, and this is another 2 track one, so it's actually quadruple the tracks just from here to here. So routing resource, so you have to be judiciously aware when to use it, when to apply this. Okay, but on clocks, we 99% we want to do it because clock nets is high switching, and we want clock integrity of clock nets per our target per our spec that we want. So
So can you elaborate more on that? Why doing that requires double width and double spacing?
yeah, so for double width, first of all, the clocks is high switching, right? High switching net. We want that to be. So we're gonna have to meet the EM rule. One of the rules we gotta meet the EM rules, right? So the wider the net is, the less chance it's gonna violate EM rules, right? We talk about here, and the extra space is the crosstalk effect. So the clock nets tend to be high switching, so it's tend to become an aggressor on as in a crosstalk effect. So I think the next slide, the last slide I have is the crosstalk effect. We'll talk about that, but that's the reason, 2 reasons that I mentioned. Until you have any additional reason you want to share?
Yeah, I want to mention about sometimes the resistance on the clock nets also can be improved with the double width. But one thing you need to know, students, that what's the drawback of using double width on clock nets? Do you know what the drawbacks, what the disadvantages of using the double width? Can someone guess? So it increase the capacitance, right?
Yep.
More YRC. Actually,
More C.
RC will be improved, but the power more C, right? More C. So you're switching more capacitance. Therefore, you increase the dynamic power, which can be very significant because clock power is about 1/3 of the whole power.
Yeah. You remember the C load? The C load is part of the dynamic power. Yeah.
Right, because you double width, and the reduction in the R will be significant. So your total RC delays will be better, but your power will be worse. Okay.
Yes. And you take up more resource, right? Yep. Okay. Thank you, Phil. Okay. Crosstalk effect. So what is crosstalk effect? We talk about it, we touch on it. I mean, we mentioned crosstalk effect quite a bit. So this is defined as unwanted coupling of signal between adjacent wires, right? So you have 2 wires going along, and then the coupling between them is what we refer to as a delta, as a crosstalk effect. So we don't want this, right? So it change your signal, it influence the outcome. So the aggressor is defined as the aggressor usually is the stronger one that causes the impact on the other net. So the other net being victim, we call it victim net. So for example, okay, so the crosstalk effect, it can speed up or slow down victim net. It also can cause unwanted glitch on victim net. So these are the 4 that I have it here. So for example, here, this is the the aggressor, right? And then this is the victim. They're switching the same direction. So you can see where the victim got speed up. The aggressor is so strong that it actually go fast. It pull up the victim along with it here. So this is in the case that it actually speed up. So if you have when the aggressor and the victim switch opposite, then you can have a slowdown. So for example, here, this is coming up, a slowdown. So it actually cause a little slowdown, a delta slowdown on the victim, right? And then in the case of glitch, where the aggressor is switching high and then you have the victim just sitting there going low, just flat. And then it pull up, then it causes a momentary pull up on the glitches and come back down. So if the glitches propagate downstream, meaning that get registered to the next in the next set of logic, like this meant to be low and it actually got registered high, then you have an issue, right? You have a unwanted glitch, and also causing the flop to capture the wrong data. Therefore, that's going to be a functional issue. Same thing here. So this is just another glitch pushing down high. It is switching low. So that's some of the impact on the crosstalk effect. So that's why we want. I mean, you can have a crosstalk effect not just between clock nets. You can have in between any nets. Okay, depending on the driver. Usually we have a driver on a big drivers on a net, and you have a weak drivers on a neck net. Then that's potentially can have a crosstalk effect. So not just between clock net and signal net, can we have between clock net and clock nets, between clock net and signal net, between signal net and signal nets. So a lot of time in the logic geometry nodes, for example, in the 3 nanometer, they have like 20x to 32x driver, 1 to 32. We normally don't use anything above 20 because that tend to become or anything 0, 1, it tend to be prone to crosstalk. So the crosstalk also effect. So it can happen between all type signals, not just the clock nets.
Yeah, there's a question by Nguyen Wen Yuen. It's a very good question.
Okay, so can we add a ground between aggressor and victim to reduce cross power? Yes, so that is one strategy is shielding. You can have shielding, or you can have shield and ground or VDD, either one, that will prevent the crosstalk. Yes.
So I do want to mention something very important. Just the speed up, the slow down, or the glitches, they happen everywhere because there are coupling caps everywhere, right? But you don't fix them all. You only fix them when they create a problems. So these crosstalk, slow down and speed up are handled by STA. STA are crosstalk aware. So you turn it on, it aware that it can simulate all these things and make sure that you, even though you have speed up and slow down, you don't have timing violations. Glitches you have everywhere, but you do a glitch analysis. This peak and the duration of this glitch, if it is small and short enough, it won't switch this gate, then you okay. You don't have to fix them all. But if it is too big, too high and too wide, it have to be a peak and the duration, then you want to fix them. But the fixing involved like separation of these two, so to minimize the cap here, or in a lot of cases, in cases like when you mentioned you have a shielding of ground and VDD, so you break, you isolate it from this aggressor to this victim, so you don't have a coupling cap between them, right? So
Yes, so thank you. Yeah, so I mentioned that, and Phil said the glitch, if that doesn't propagate downstream, meaning that get registered at the next gate, then you don't have to worry about it. That's what I mean by propagate downstream. Yeah. I haven't talked about how to fix them, but I can really say one of the ways shielding. The other way is, for example, if the aggressor is driver is too big and you can tolerate, meaning still meet timing, you can downsize the aggressor, or you can upsize the victims, the victims, or by separating the nets, shielding or spacing them out also help fix it. Okay, but usually, yeah, the tool will do an analysis on when we enable the even in Innovus, there we can turn on the SI, right? On the crosstalk, I mean, then it will do analysis and we'll do the routing, and it actually will try to keep it away each other as best as it
Yeah,
can.
yeah, it will fix, but it's important for you to understand, yeah, how these things work so that you won't just push a button, right?
Yeah. So yeah, so I mean, you turn it on, you understand this, because when it breaks, meaning that doesn't work the way expected, you have issue, it doesn't fix everything for you, okay? So you have to, that's when your engineering skill come in, is that you understand, okay, how do I fix this manually? So tool can't fix it. You have to go understand it and ready to fix it manually, or change the setting or whatnot, how to drive a tool to fix it, not fix it manually. Okay, so that's at the end. We're kind of 7 minutes over. I thank you for your time, and next week we will dive into the second part, and then we'll talk about the labs, the first lab. Okay. Thank you, Phil Wu, for chiming in and explain some of the concept.
Sure.
The recording
Thank you,
has
Danny, for keeping
stopped.
timing, and everybody have a great day.